Hey everyone, let's start. Welcome to XCamp 2023 February USACO Solution Discussion. This is Charlie Guo. I'm the co-founder and principal of XCamp. Today, I will give you a quick introduction about XCamp. Then we will give you the USACO contest tutorial. After that, we will give you an introduction on our classes and how to prepare next USACO. XCamp is a Silicon Valley-based coding academy. We have classes from beginner to master and to IOI level. Our curriculum was developed by seasoned coaches, including IOI medalists, USACO veterans, etc. We have proven records. We provide solid knowledge on data structure and algorithms for the students. We have been 4 USACO campers in the last season. For this season, we have 2 students joined top 10 in the Platinum division. For our coding problem and solutions, we provide beginner level for the kids to love coding. Then we provide algorithm and data structure foundations for the students to have complete knowledge. After that, some students might go to competitions. Some of you may follow this direction. Some of you might do more coding as engineer in academia or industry to have some lower bound of your life skills to be a software engineer. Today, for the bronze session, we have Max. He's the our USACO Grandmaster class coach, also the ICPC World Finalist. In the ICPC finished last week. Their team, they're the top 1, I think, in the Southwest America. Now, I would like to turn the screen class to Max now. Max, turn to you.
Yeah, thank you, Charlie. Let me share my screen. Okay, so let's begin by talking about the first problem from the USACO Bronze contest. The first problem was about Farmer John giving hay bales to cows. And the idea is that there are a bunch of days, there are T days, and on each day there is so we have a day. So we have a bunch of inputs of the form. We have a bunch of inputs of the form DI and BI, which means that on day DI, there will be BI hay bales added to like some sort of supply. And then each day, Bessie will try to eat a hay bale if possible. So basically each day, so on each day, so if I guess you can say if the amount of hay bales is greater than, if there is at least 1 hay bale, then Bessie will eat one. And then also if there's if it's on like day DI, then we get plus BI hay bales. And so the question is, throughout these entire T days, how many hay bales does Bessie end up eating? So one idea is we could go through each day, right? Let's say we start with day 1. If there are no hay bales, then Bessie doesn't eat a hay bale. Day 2, day 3, day 4, we just go through every single day. And then let's say we reach, let's say there's an input. Let's say the first input is, let's do an example here. So one example they have is, let's say we have 2 inputs. There's 1, 2, meaning that on day 1, there are 2 hay bales added, and 5, 10, meaning that on day 5, 10 hay bales are added. Then what happens is on day 1, so this is day, so these are, let's go ahead and go here now. These are the days. So on day 1, there are 2 hay bales added, and then Bessie will eat 1. So therefore Bessie has eaten 1 hay bale so far. On the next day, there is 1 hay bale left. Bessie will eat 1 again. So now there's 2 hay bales left. On the next day, on day 3, there are no hay bales available. So Bessie will not eat a hay bale. And the same for day 4, there is no hay bales. And then we get to day 5. On day 5, we have an input that says we get plus 10, right? And then Bessie will eat 1. So now Bessie eats another hay bale. So that's kind of how the process goes. We go through each day, and then if there's an input that says on this day we're going to add BI hay bales, then we just add it. So like some sort of counter, some sort of variable. So we have some like counter that keeps track of how many hay bales we have total, and each day we add BI to it if there's an input for that, and then we subtract 1 if it's greater than 0 and add 1 to our answer. This is a little bit too slow because the t, this total number of days, could be at most 10 to the 14. So this is an O of t solution will be iterated over every single day, will be a little too slow. So this is O of t. So let's try to make this a little bit faster. And to make this a little faster, we simply note that on a lot of the days, because there are only at most n inputs, right? N inputs, where n is much smaller. N is up to 10 to the 5. So yeah, so a lot of the days we're not actually receiving any new hay bales, so we know exactly what's going to happen, which is that we simply minus 1, minus 1, minus 1, and so on. So we don't have to really like simulate every single day. We can instead skip to whenever new hay bales are added, and those are the only cases where something changes. Otherwise, we know we just subtract like as many days as we can. So to be more precise, day D1, on day D1, we get plus B1. So before that, any day before D1, we have no hay bales because we didn't start with any. So there's nothing added to our answer. Then when we get to D2 and plus B2, we know that in between this time, there were D2 minus D1 days. And so we basically say that, okay, and between those days, we had B1 hay bales total. So if B1 was greater than or equal to D2 minus D1, then we are able to eat a hay bale on each day. So we simply add D2 minus D1 to our answer, and then we subtract that much from our supply. So this is add to here. This is add to answer, and then subtract from our supply. And the other case, what is the other case? The other case is when B is less than D2 minus D1, then what happens? Well, we're not going to have hay bales on every single day. We're going to run out before the days are over. So, but this case is also just we eat all B hay bales available. So we add B to the answer, and then we subtract B from our supply, and our supply is 0. We have 2 answer and from supply. And then when we get to day D2, we just add B2 to our supply, and then we consider D3 and onwards. And so it's the same idea again. And so by doing this, we only have to visit each of the n days where something changes, and then we can just quickly simulate in between by adding the appropriate amount to our answer and taking away from our supply. And so this gets us to an O of n solution. Actually, I think we might need O of n log n because we have to sort the initial inputs of DI and BI. or actually, the inputs guarantees that they're already sorted, actually. So the input guarantees that like D1 is less than D2 is less than, and so on. So actually, we can just do O of n because they already sorted it for us in the input. So we have an O of n solution. And that will be fast enough to solve all of the test cases. So does anyone have any questions on the first problem? Yeah, perfect. Let's move on to the second problem then. Second problem, what is the situation in the second problem? So we have, we essentially have this n by n canvas and a k by k grid, or k by k stamp. N by n canvas, k by k stamp. So our canvas is going to be some square grid, and at the end we want certain cells to be painted or stamped. And we use asterisks in the input. So we have a certain cells that we would like to be stamped by the end of this process. And then the stamp is also similar, except the stamp is not of size n, it is of size k, where k can be less than or equal to n. And so our stamp might be, maybe let's say it's a 2x2 size stamp, and it stamps these particular places. And now what we can do is we initially have empty canvas, and we can take this stamp and we can place it on top of somewhere on our canvas, and we can stamp that part. So if we place it on top of here, then it will paint this cell, and this cell, because that is the shape of our stamp. Now I'm also allowed to rotate this stamp. So I can also rotate it so that it looks like, I can rotate this stamp so it looks like this. And then plant it on top of, say, here. So that I'll stamp here, here, and here. And then finally, I can also put a stamp on top of here. I can also stamp here and cover these. And so you can notice that we're allowed to cover the same spot more than once. It's just that for the blank spots, we need to make sure we never cover them, because we want to make sure they're blank by the end of this. And so the question is, if I can rotate my stamp and paint a bunch of squares on this canvas, then am I able to create the final canvas pattern with the stamp? It's a yes or no question. And bounds, because bounds are pretty important. N is less than or equal to 20. So with n less than or equal to 20, we actually have quite a lot of leeway with our solution. So we can look for something maybe pretty simple, or just try to brute force or try a bunch of possibilities. So the key observation is that if we are able to stamp a spot, let's say we are this cell here, right? If this alignment here, we stamp this 2x2 area. If we are able to do that, it doesn't conflict. We don't stamp any cells that aren't supposed to be stamped. We only stamp cells that are painted in the final configuration. If we are allowed to do that, then there's no reason not to. We might as well. From a greedy perspective, we might as well stamp everywhere that we are allowed to stamp, because that just increases the chance that we get closer to the final pattern. And so what do I mean by that? Let's say I take this situation here, right? Then let's go back to the cell. So if I look at this 2x2, this I cannot stamp using this pattern, because that would paint these two empty cells which we don't want to be painted. Here, it would paint only painted cells. So yeah, we might as well go ahead and stamp. Let's do that. I'm going to actually make this example a little more complicated so that we get some more examples of places where we can stamp. So here, if we have this pattern, we're considering it, then we should not stamp here, right? Similarly, we should not stamp here. We should stamp here, or we might not have to, but we might as well stamp here, because all the cells that it covers are painted cells. So just go ahead and stamp that. We shouldn't stamp here. Fast forward, we might as well stamp here because we can. So that's kind of the idea, is we take this pattern and we just stamp everywhere that we can possibly stamp. And then we'll rotate it so it looks like this, and we'll do the same logic again with this rotated version. Let's stamp every single place possible. And then similarly here, let's also do that for this rotation. And with the final rotation, let's also do it for that. So basically for all 4 rotations, we iterate through the entire grid canvas, and we on every single possible alignment of the K by K stamp, and we just check. We can naively brute force over the stamp window and check in every single place where a stamp is, in every single place in the stamp pattern, is the corresponding cell painted or covered in the final canvas. And if all of them are, then we will stamp that spot. And then at the end, after we do all possible stamps, we just go through one more time and see if the final stampage or the final pattern that we created matches the pattern in the canvas. And so what is the complexity of the solution? We iterate over every single possible alignment for each of them. So there will be a ×4 factor, but it's time complexity. So we won't analyze ×4. So we iterate over every single alignment. So there are n minus k possible alignments, n minus k plus 1 technically, but it's time complexity. So actually I'll simplify just to n squared to keep it simple. So n minus k squared or n squared. And for each alignment, it takes k squared time to iterate over every single cell inside the window. So it's n squared k squared. And this is fast enough because the bounds are quite small for this problem. Any questions on the second problem? All right. Let's move on to our third problem then. The third problem, so it is a subscription service. Yeah, I don't really have a good link that I can provide because they're not public. I'm just looking off of images I have saved on my computer. So I'm just describing it again out loud. Hopefully that's enough. Yeah, so the third problem was about subscriptions, and the idea is that there are a bunch of days. So Bessie is watching TV, and there's a bunch of days where she wants to have the subscription. So the days D1, D2, D3, and so on. So on these days, up to DN. So on each of these days, Bessie wants to watch TV, and what she can do is she can purchase a subscription for a contiguous amount of time. And if she purchases let's say she purchases a subscription for T days in a row, then it will cost her T plus K. That is the cost of a subscription of length T contiguous days. And she can buy as many subscriptions as she wants. She can end her previous one and then start a new one a couple of days later. She can basically do this however she wants, but it basically just costs K, a flat fee of K for each time she starts a new subscription, plus the amount of time within the subscription interval. And so the question is, what is the minimum amount of basically what's the minimum cost she needs to be able to watch TV on all of her desired days? And for bounds, n is less than or equal to 10 to the 5. And the d's are up to the di are up to 10 to the 14. So kind of similar to the first problem, we cannot iterate over every single day individually in the full solution. We'll instead only be able to iterate over the di's. So let's look at this problem from a greedy perspective. So the first day is D1. There's no advantage to starting a subscription earlier than D1, right? Because you don't need to watch TV before D1. And you're starting a subscription earlier only costs more because each extra day you add to your subscription is at least a +1 in cost. We might as well start our first subscription on day D1. Now let's fast forward to D2. The question is, should we include D2 in the same subscription? So should we extend our old subscription all the way up to D2? Or should we just end on D1 and start a new one at D2? Basically, those are the two options we have. Because if we are to extend our old subscription to D2, then we just take that, we go all the way up to here, right? And this will cost D2 minus D1 +1 and then plus K. Or our other option is we end our old subscription. If we're going to end it, we might as well end it right after D1, and then we start a new subscription starting from D2. And the alternative cost of that would be it would be 1 plus 1, so 2, plus 2K. As you can see here, what we're really comparing is because this 1, we can think of it as originally here, this initially already costed to start a subscription there originally at D1, this already costed 1 for the number of days plus K. And so the extra cost that is incurred when we consider day 2 now is either we add to our old subscriptions that adds a cost of D2 minus D1, or starting a new subscription, which adds a cost of K plus 1. And so now when we look at these two, value quantities, this is like how much we add to our total cost, depending on which choice we make. Then we just make a greedy choice. If D2 minus D1 is less than K plus 1, then it is greedily optimal to keep the same subscription, like extend the subscription. Otherwise, we start a new subscription. So essentially, we're just adding the minimum of D2 minus D1 and K plus 1 to our answer. And actually, after that, we get a D3, we apply the same logic, right? We either extend our subscription onwards to D3, which costs D3 minus D2, or we start a new subscription, which costs K plus 1. And so our greedy just ends up being quite simple. At the end of the day, we're just doing a for loop over all DI. We're taking the sum of from 1, or I'll say from 2 to n of minimum of DI minus DI minus 1 or K plus 1. And then plus an additional K plus 1 for the first one. That would be our answer. So this works in O of n. Any questions on this problem? All right, then, yeah, so in that case, oh wait, hold up, yeah. Yeah, so in terms of code, it actually ends up being quite concise, right? This computing this is essentially a for loop. I'll be literally rewriting like a for loop. After I take in the input, I'll be doing like a for loop from, I guess in the code, it would be, we would usually 0 index it. So it would be from like I from 1 to n. We add to our answer minimum of, what was it, di minus di minus 1 and K plus 1. Initially, we have answer is equal to K plus 1. All right, any other questions? All right, then let's turn it back. Let's turn it back to these slides.
Yeah, thank you. I think there are a couple questions. Let me see.
Yeah.
Max, do you see that chat?
Yeah, I see it now. Yeah. I guess I'm assuming when you say I'm assuming you're referring to the Python function when you say map like with parens, because that's the only context I know for that function. I guess I mean I think you can like technically do everything in Python with just loops. I think it's just a matter of how much fancy Python syntax you choose to use. Yeah. I mean generally I use C++, so I'm not too familiar with the intricacies of Python, how to write the most efficient or shortest code. Yeah.
Thank you, Max. Students, any other questions? Okay, let me have a last slide to share with you. Yeah, if some of you passed this USACO bronze this time, congratulations. If not, we prepare some classes for you. The first one, we have the March public USACO mock test. It's on March 18th from 4 to 8 p.m. Eastern time. So, we have all these levels. You can have extra practice before the last US Open contest this year. Also, we have summer on-site camp. It's the end of July, 2 weeks. So this can boost your performance. It is in San Jose. We have limited seats, 20 students for each level. Finally, we have weekly weekend class. Our spring quarter starts on April 1st. Our summer quarter starts on June 24th. These are all 10-week online class. You have 2-hour instructions every week. Also, you have office hours and homework. Hopefully, these kind of resources can help you keep improving learning in coding. I think that's all for this session. Also, we have this recorded on YouTube. Also, this kind of a broadcast in YouTube too. You can find the video there. If you have any questions, you can review this session later. Again, thank you, Max. Thank you for helping us explain these problems. Yeah. Wish you all have a good night.